Students, welcome to today's chemistry class. Today I am going to explain you about the colligative properties. Previous class I have explained you about the solutions and the continuation of that is colligative properties. What are colligative properties? Here you can understand colli from Latin co-mean together, colligative. So to bind, so from a Latin co-mean together and ligare means to bind. So, colligative properties are the properties which depend upon number of solute particles in solution irrespective of their nature. Colligative properties are generally explained for dilute solutions. So, dilute solution containing non-volatile solute and do not depend upon the nature of the solute dissolved in that solution. They depend only upon the concentration, that is number of solute particles present in the solution. That is called as colligative property. Colligative property, certain properties of the dilute solution is a colligative property. So the properties which depend upon the number of solute particles, the solutions containing non-volatile solute, but they don't depend upon the nature of the solute. They depend upon the number of solute particles in that solution is called as a colligative property. That property of a dilute solution which depend upon the number of number of the solute particles and not the nature of the solute particles is called colligative property. This colligative property, it is of four types: lowering of vapor pressure, osmotic pressure, elevation of boiling point, depression of freezing point of the solvent. These are the four colligative properties. Now, I'm going to explain you about the relative lowering of vapor pressure. It is the ratio of lowering of vapor pressure to the vapor pressure of the pure solvent. It is the what is lowering of vapor pressure is P naught minus Pa is lowering of vapor pressure. Ratio of lowering of vapor pressure to the vapor pressure of the pure solvent is called relative lowering of vapor pressure. And relative lowering of vapor pressure, which is containing the non-volatile solute, it is equal to the mole fraction of the solute in the solution. So ratio of lowering of vapor pressure present to the vapor pressure of the pure solvent. The relative lowering of vapor pressure of the solution containing non-volatile solute, it is equal to mole fraction of solute in the solution, is called relative lowering of vapor pressure. Okay, P naught minus Pa by P naught is equal to RLBP. P naught minus Pa by Pa is equal, P naught A is equal to RL. So P naught minus Pa by P naught A is equal to Np by Na plus Nb. For dilute solutions, Nb is very less. Therefore, it is almost less. Nb is very less than Na. Hence, P naught minus Pa by P naught is equal to Nb by Na. P naught minus Pa by P naught is equal to Nb is Wp by Mb. Na is Wa by Mb. So P naught minus Pa by P naught is equal to Wp by Mb by Wa by Mb. Now once if you reverse multiply it, you get Wp by Mb into Ma by Wa. Next, Mb is equal to, this Mb is equal to molecular weight of solute. This whole term comes here on Mr. Notes. So Mb is equal to Wp by Wa into Ma into P naught A by P naught minus Pa. The above expression, it is used to find molecular weight of unknown solute dissolved in a given solvent, where Wp Wa is equal to mass of the solute and solvent respectively. Mb and Ma are molecular weight of solute and solvent respectively. And using Ostwald-Walker method, we can determine RLVP. Using the Ostwald-Walker method, we can determine the relative lowering of vapor pressure. So this lowering of vapor pressure is a colligative property and it has limitations with respect to Raoult's law. How we have determined using this lowering of vapor pressure, we can determine the molecular weight of the solute. Let me give a brief introduction. Yeah, I'm going to give you a brief introduction about the quarterly method, Ostwald-Walker method, by which we can measure the lowering of vapor pressure. Ostwald-Walker method. This Ostwald-Walker method, I'll just give you a brief introduction how to determine experimentally RLVP. So, Ostwald-Walker method, you have apparatus for measuring the. In this method, so there are in this method, Ostwald-Walker method, devised to direct for determining the RLVP. This method, Ostwald and Walker's dynamic method, gas saturation method, or it is a transpiration method. And in this method, a stream of dry air is passed successively through set of weighed bulbs containing the solution, then through the set of weighed bulbs containing the pure solvent, and finally a set of weighed U tubes containing a reagent which can absorb the vapor of the solvent. So it contains anhydrous calcium chloride or concentrated sulfuric acid. If the solvent used in the water, the bulbs containing the solution and the solvent are placed in the thermostat maintained at a particular temperature, steam air may be passed gradually and ensures the saturation with vapors. So when dry air passes through the solution, it gets saturated with the vapor present over the solution, or until the pressure becomes equal to the vapor pressure of the solution. So the weight of the solvent lost by the solution bulb is proportional to the vapor pressure of the solution. So if a diagram is there, you can more clearly understand this Ostwald-Walker method. Ostwald-Walker method is one of the device. It is the gas saturation method and the transpiration method in order to calculate the RLVP, relative lowering of the vapor pressure. Experimentally, we can determine. So there we can see loss of weight of the solution in the bulbs, loss of weight of the solvent bulbs, loss in weight of the solution bulbs, loss in weight of the solvent bulbs measured, loss in weight of the solution bulb plus loss in weight of the solvent bulb is measured. And depending on this, we get the relative lowering of vapor pressure. So relative lowering of vapor pressure is equal to loss in weight of the solvent bulb by loss in weight of the both solvent and the solution. That way, we measure the loss in weight of solvent bulb by gain in weight of the calcium chloride U tubes. So it is possible to calculate the RLVP. So finally, what you do is after doing the Walker method, we calculate loss in weight of the solvent bulb by loss in weight of the both solvent and the solution. Now, this is the way we do. So here, this is the RLVP mathematically we've done, and I have explained you briefly about the Ostwald-Walker method to determine the relative lowering of vapor pressure. Now we'll see elevation of boiling temperature. Elevation of boiling temperature delta T. Boiling point of a liquid is the temperature at which its vapor pressure becomes equal to atmospheric pressure. You know, when will a liquid boil? What is a boiling temperature? When will a liquid boil? So liquid boils, the boiling temperature of the liquid. When will it boil? When the atmosphere, you take a liquid, you put it on, you give it the temperature. It starts boiling after some time. During summer, it boils quickly, and during winter, it will take some time. Why is that happening so? It is because it has to reach the boiling temperature. So what happens? Why it is boiling temperature? What is the difference? It is because when the atmospheric pressure is equal to the vapor pressure of the solution, when atmospheric pressure of the solution is equal to vapor pressure of the solution, then the liquid starts boiling. So that is known as the boiling temperature for that particular liquid. And we are having 100 degrees for water. So different liquids have different boiling temperatures. A boiling point of a liquid is the temperature at which vapor pressure is equal to atmospheric, as you all know. Now, what is elevation in boiling temperature? As vapor pressure of solution containing non-volatile solute, you take a solution, it is having non-volatile solute. You boil it. Now, the vapor pressure of the solution containing non-volatile solute, it is lower than that of pure solvent. For example, you take water 100 degrees to boil. When you add a non-volatile solute, it will take nearly 105 degrees. So the vapor pressure of the solution containing non-volatile solute, it is lower than that of the pure solvent. So its boiling will be higher. Vapor pressure will be lower, boiling will be higher than that of the pure solvent. Increase in boiling temperature is nothing but elevation in boiling. The increase in boiling temperature. You take a pure water, it is 100 degrees. To this, you add some solute. After addition of solute, it will take some more time to boil. It may take nearly 103 degrees. So pure solvent it is 100, and after addition of non-volatile solute, it becomes a solution and the temperature is 103 degrees. It is 103 degrees. So the difference in the boiling temperature, 103 minus 100, that is elevation of boiling point. That is delta TB. That is called as the delta T. Delta TB is equal to TB minus TB naught. TB is the boiling temperature of solution. T naught B is the boiling temperature of the pure solvent. Delta TB is equal to Kb into M, molarity. So you get delta TB is equal to TB minus TB naught B, and delta TB is equal to Kb into M. This is molar. This is called ebullioscopic molar elevation constant or ebullioscopic constant. Ebullioscopic constant or molar elevation constant. Here we draw a graph. See this graph, temperature versus vapor pressure. I have drawn. Now for the solvent, this is the temperature. Here is the boiling temperature, 100 degrees. And after addition, for solution you are getting near 103 or 110 you get. This is TB. This is the boiling temperature of solvent T naught B, and this is the boiling temperature of the solution, that is TB. Now the difference in TB minus T naught B is delta TB. It is delta TB. This is called as the elevation of boiling temperature. See, it has to be 100, it has increased to 100. So the change in this boiling temperature is elevation in boiling temperature. Okay, so this is delta T. Now the formula TB delta TB is equal to TB minus T naught B. So delta TB is equal to KB into M. So delta TB is equal to TB minus T naught B. So delta TB is equal to delta into KB into M. So TB minus T naught B is delta TB. Okay, so delta TB finally is equal to KB into M. So Kb is the molar elevation constant or ebullioscopic constant, and the molecular mass of solute can be calculated here. Using the elevation of boiling temperature, we can calculate the molecular weight of the solute. So previously, for lowering of vapor pressure also we have calculated. Relative lowering of vapor pressure we have calculated. Using that one, I have calculated the molecular weight of the solute in a solution. Now, for this one also we'll see delta TB is equal to KB into WB into 1000 by MB into WA. So delta TB is equal to KB into WB into 1000 by MB into WA. MB is equal to KB into MB is equal to delta TB comes down. So MB is equal to KB into WB by WA into 1000 by delta TB. So using this formula, we can calculate the molecular weight of the solute. So this is the second colligative property using which we can calculate the molecular weight of solute. Now, MB, MB is the molecular weight of solute. KB, KB is the ebullioscopic point. Next, WB is the weight of the solute and W is the weight of the solvent. Delta TB is the ebullioscopic point. Next, the boiling temperature of elevation of the solution is determined by Cottrell method or Landsberg's method. I'm going to give you a brief explanation about the elevation of boiling point determination experimentally by Cottrell method. See, the boiling temperature, boiling point we have defined. Now, elevation of boiling temperature also we have defined. Using that one, I have calculated the molecular weight, molar elevation constant. How will you define? Molar elevation constant, it can be defined as molar elevation constant, it can be defined as Kp. Elevation in boiling point produced by dissolving 1 mole of any solute in 1 kg of solvent. I am repeating, elevation in boiling point, elevation in molar elevation constant is defined as elevation in boiling point produced by dissolving 1 mole of any solute in 1 kg of solvent. Is called molar elevation constant. Now, using Cottrell method also, we have determined this method. Cottrell method simply you'll be having here Landberg methods or Cottrell method you can take. Cottrell method consists graduated boiling tube containing solvent or solution, condenser filter, and a graduated tube. And the condenser returns the vaporized solvent to the boiling tube. Thereupon, the weighed amount of the solute is added to the solvent and boiling point of the solution is determined as that of solvent. So volume of the solution is noted from density of the solution. Mass of the solvent present in that can be calculated. Okay. So using this one also, yeah, we can do. You have a thermometer and a small inverted funnel that is 3 gadgets, and you can calculate delta TB, that is TB minus T naught means delta TB. That is difference in the elevation. And using this formula, you can directly calculate the molecular weight. That is the experimental way of determining the molar the elevation of the boiling. Now we'll see the fourth colligative property, depression of freezing point, delta T. Previously delta TB, now delta T. It is quite reverse. Delta TB is TB minus T naught B. The boiling temperature of solution minus boiling temperature of the pure solvent is elevation of boiling. Now depression of freezing point, it's quite reverse here. Delta TF is equal to T naught F minus TF. Okay. Pure solvent freezing temperature minus freezing temperature of the solution. You get depression in freezing point. Okay, so freezing point of a liquid is the temperature at which vapor pressure of solvent in its liquid and solid phase becomes equal. So vapor pressure of the solvent, vapor pressure of the liquid and the solvent phase are equal is the freezing point. So the vapor pressure is equal. There the atmospheric pressure is equal to the vapor pressure of the solution. That is boiling. Now vapor pressure of the pure solvent and the solid phase, both of them gets equal. That is called freezing. As we know, the vapor pressure of the solution contains non-volatile solute. It is lower than that of pure solvent. So I've told you delta TF is equal to T naught F minus TF. Okay, so pure solvent freezing temperature is more, and for the pure solution it is getting decreased. As you add the solute, the freezing temperature still decreases. So what is the depression in freezing temperature delta TF? T naught F minus Tf. So vapor pressure of solution containing non-volatile solute is lower than that of pure solvent. Solid form gets separated out at lower temperature as it is shown here. Yeah. I've drawn the graph, y-axis, x-axis. Now here, this is the temperature and this is vapor pressure. Now pure solvent, you're having this is the boiling temperature here. Pure solvent freezing, it's coming down. Freezing temperature is here. And after addition of some solute, it becomes a solution and its vapor pressure is Tf and it is still decreased. The temperature is from here it is getting still decreased, that is Tf. So T naught F minus Tf is depression in freezing temperature. Delta Tf is equal to Kf into M. Delta Tf is equal to Kf into M. So M is equal to, now delta Tf is equal to Kf and M is equal to Kf in Wb by Mb into 1000 by Mb. Molality. M is nothing but molality. Okay, the formula molality is equal to Kf into Wb by Mb into 1000 by Wb. Now after interchanging Mb here and here, see you get delta Mb is equal to delta Mb is equal to, here in place of M we'll substitute this whole term. Mb is equal to Kf into Mb is equal to, capital Mb is equal to Kf into Wb. Kf into Wb into 1000 by Tf into Wa. Tf into Wa. After interchanging, get the molecular mass here in this. So Kf is the molar elevation constant, molar depression of freezing point. Here also, molecular weight of the solute, molecular weight of the, weight of the solute, molecular weight of the solute. Delta Tv is the hygroscopic point. W is the weight of the solvent. Mu is the weight of the solvent. Okay. And here also the same. Weight of the solute is Wb. Molecular weight of the solute is Mb. And Wa is the weight of the solvent. Kf is the molar, Kf is the molar depression. This is the molar depression freezing constant or cryoscopic point. Contains cryoscopic point. Now, Kf has a unit like this. Kb is equal to Ma into RT not B square by H. So, molar enthalpy of the fusion is delta HF. Molar enthalpy of vaporization is HV. So, Tf freezing point of solvent. Tb is the boiling temperature of the. So, Kb and Kf values, previously I didn't give you Kb value, now it's given, and Kf value. So, molar depression freezing constant value is this one, and molar elevation one constant is this one. So, HV vaporization, HF freezing point. Okay, fusion, HF for fusion, freezing. Now, you can calculate ethylene glycol is usually added to water in the radiator to lower the freezing point. This is anti-freezing solution. Ethylene glycol we add, the freezing point is still decreasing. Now that solution is anti-freezing solution. You take a common salt NaCl and anhydrous calcium chloride to clear the snow, and it's a common salt and anhydrous are used to clear the snow on the roads. This is an application part because it depresses the freezing point of water. Okay, once if you spray that NaCl and anhydrous calcium chloride, what the freezing point will decrease. So it turns into water. The roads will get more clear. That is an application part. Now freezing point depression is determined by Beckman method or Rast method. I'm going to give you a brief introduction about the Beckman method and the Rast method. Using the Beckman method and the Rast method, we can determine the depression of the freezing point. Beckman method, that was the earlier method. calculate. It's a very simple method, Beckman method. The Rast-Camphor method can also be used. So Rast method is more advantageous. It is very sensitive. So in there we are having a freezing tube. It is fitted to the Beckman thermometer and platinum stirrer. The outer glass tube you are having, which the inner freezing tube 8 spaces there in between them. So there is a glass jar inverted. So according to the procedure you do, and finally you get the weight of the solute and solvent with the depression freezing point. You know the weight of the solute and the solvent and depression freezing point. And depending on that, we can calculate the KF, delta TF value. We can calculate the change in the delta TF value with the depression freezing point. We can calculate. I'm just going to give you briefly about the advantages of a Rast method over the Beckman method. See, instead of this Beckman method, Rast method is more preferred. Why? In order to determine experimentally, Rast method is more because it is very sensitive and even a ordinary temperature can be used in place of Beckman. See, for Beckman method, we have to take Beckman thermometer. The Rast method you can do even with the simple thermometer. And small quantity of the substance is required in the Rast method. Micro cryoscopic method also required because very less amount of sample is used in order to determine the depression and freezing point. Now we'll see the fourth colligative property, osmosis. What is osmosis and osmotic pressure? Osmosis is the phenomenon of spontaneous flow of solvent molecules through a semi-permeable membrane from pure solvent to solution or from dilute solution to concentrated solution. So what is osmosis? Osmosis is flow of solvent molecules through semi-permeable membrane from low concentration to high concentration. From low concentration to high concentration it takes place, and it is observed by Abby Norrit, scientist Abby Norrit. Some of the natural semi-permeable membranes are animal bladder, cell membrane, okay, copper ferrocyanide, artificial semi-membrane. This can work out even for the non-aqueous solutions. Now, what is osmotic pressure? We'll see what is endoosmosis, what is exoosmosis, and what is osmotic pressure. So, exoosmosis, it is the outward flow of water or solvent from cell through semi-permeable membrane. Outward coming is exoosmosis. The outward flow of water of the solvent from cell through semi-permeable membrane, and that is from low concentration to high concentration is exoosmosis. Now, what is endoosmosis? Inward flow of water or solvent from a cell through a semi-permeable membrane. The hydrostatic pressure developed on the solution, which prevents the osmosis of pure solvent into the solution through semi-permeable membrane, is called osmotic pressure. Okay, so you know what is endoosmosis? Is inward flow of water from cell through semi-permeable. Inward flow of water from cell. Outward flow of water from cell is semi-permeable. Next, what is osmotic pressure? Hydrostatic pressure developed on solution, which prevents the osmosis of pure solvent into solution through semi-permeable membrane, is called osmotic. A hydrostatic pressure, which is being developed on the solution to prevent the osmosis, okay, from low concentration to high concentration. So that the pressure, hydrostatic pressure, which stops, which prevents osmosis, osmotic pressure. It is denoted by pi. Pi. It is denoted by RCT. Pi is equal to RCT. C is nothing but the concentration MB by W. Again, you know, N and number of moles, weight by molecular weight is number of moles of the solute. Here, WB by MB to V. So I'm substituting in place of this one. Pi is equal to R into WP by MB into V into T. That is the formula. Now MB on going to the left side and pi comes to the right side. MB is equal to WP by V by pi into RT. WP RT by pi. Pi is equal to dRT by M, where D is the mass by volume. See, density, weight by volume. W by V is D. Okay, pi is equal to D into RT by V. Next, here density R is the solution constant. Previously for gases it is the gas constant, and for solution it is solution constant. And T is the temperature, MB is the molar mass of solute. Osmotic pressure is determined by the first method, Berkeley-Hartley method. This is a very good method, and generally for our degree syllabus this is being explained. Now Moser-Fuzzer methods, and on basing on the osmotic pressure, the solutions can be calculated are of different types. We'll see what are the different types. Hypertonic solution. Before going with that Berkeley-Hartley method, how it is useful, we'll see. That is the experimental method. Berkeley-Hartley method is an experimental way by which we calculate the osmotic pressure, and basing and using this osmotic pressure, we are able to calculate the molecular weight of the solute. We are able to calculate the molecular weight of the solute. Berkeley-Hartley method we employ. So in the Berkeley-Hartley method, it's an accurate, quick method. It is an accurate, quick method. Involves determination of excess of pressure is applied on the solvent to prevent the entry of solvent solutions to stop osmosis or osmotic pressure. See, you have it consists of a porous pot, electrolytically deposited copper ferrocyanide, a semi-permeable membrane on its walls, and one side it is connected to capillary tube, a dropping funnel on the other side. The porous part is fitted into the tube and dropping funnel on the other side. This porous part is fitted into the tube T and dropping funnel on the other side. The porous part, again, it's fitted to the gunmetal jacket provided with 8 piston, and the piston in turn is attached to the pressure gauge. So, with whatever pressure the osmosis getting stopped is noted by the pressure gauge. So, the porous part is fitted and the jacket is filled with the solution. Porous part with water and jacket filled with the solution. So, what is the osmotic pressure development? We can calculate using this method, that is Berkeley-Hartley method. And thereupon you can calculate the molecular weight of the solute using the osmotic pressure. Now, different types of solutions. Hypertonic solution. The solution is called hypertonic if its osmotic pressure is higher than that of solution from which it is separated by semi-permeable. If osmotic pressure is higher than the solution, that of solution from which we are separating, that is hypertonic. Its concentration is more, osmotic pressure is more than that of the solution from which we are separating is called as hypertonic solution. See, in a plant cells placed in a hypertonic solution, fluid from plant cell comes out. Shell gets strained, that is plasmolysis. Okay, so and hypotonic. The solution is called hypotonic if its osmotic pressure is lower than that of the solution. Solution whose concentration it is osmotic pressure is lower than that of the solution from which it is getting separated is hypotonic solution. So what are isotonic solutions? Two solutions are called isotonic solutions. They exert same osmotic pressure. Yeah, these solutions have same molecular molar concentration, 0.91 solution, and pure NaCl is isotonic with human RBC. That is isotonic solution. Osmotic pressure, it's the best method to determine the molecular mass of polymers, where we are using. And what is reverse osmosis? External pressure applied on the solution is more than the osmotic pressure. The solvent flows from the solution to the pure solvent. And this is called reverse osmosis. Desalination of the seawater is done by reverse osmosis. Desalination. The salt content is removed by reverse osmosis. Okay, when excess of pressure is applied on the solution, it moves in a reverse way. That to that of osmosis from high concentration to low concentration. That is low reverse osmosis. Now there is abnormal masses. You can see association of molecules and dissociation of molecules. So due to that, you can observe abnormal masses. For this, a factor is introduced, that is Van factor I. A ratio of observed value of colligative property to the calculated value of the colligative. Observed value by calculated value. That is called I Van factor. Okay. So delta TB is equal to I into KB into M. So Van factor related to the elevation of boiling point. For depression of boiling temperature, delta TF is equal to I into KF into M. Pi is equal to ICRT. So P naught by Pi is equal to IX. So this is the way it is related. Delta TB is related, delta TF is related, pi is related, and relative lowering of equation is related. Okay. These are the four relations of colligative properties with Van factor. Now, degree of dissociation and Van factor, how it is there for abnormal masses. See, alpha is equal to I minus 1 by n minus 1. This is the formula you have to apply the Van factor for degree of dissociation. Alpha is a degree of dissociation and Van factor. The relation here. Alpha is equal to I minus 1 by n minus 1. Now for the degree of association, what and Van factor, how is the relation? You see here. Alpha is equal to I minus 1 by n minus 1. This is the way Van factor and the degree of dissociation and association associated. So I hope everybody have understood this class. I gave you a brief picture of the colligative properties, relative vapor pressure, relative lowering of vapor pressure, elevation of boiling temperature, depression and freezing temperature, osmotic pressure. And what is Van factor? Abnormal masses we can see association, dissociation. And what is a factor that is governing this abnormal masses? Van factor. How it is related to the four colligative properties, the equations. Okay. Thank you, everybody. I hope everybody have understood today's class.